relatively new in science. He started here in the fall. Before that, he was at MIT, right? And he worked with Piotr Index, who's a guy some of us know. And so you can kind of, if you know Piotr, you probably get a little sense of what he's doing. Some of it is related to the course he's teaching this semester, which is basically fast algorithms for really big data, that sort of thing. He's worked on privacy, on search and retrieval, and today he's going to be talking about searching, I guess, but for distribution, so we'll hear about that. And he's a huge fan of spicy food, so I think, sounds like he'll fit right in. We got some spicy pizza over there. Okay.
All right. Yeah, thanks everyone for coming, and please feel free to stop me anytime. Happy to take any questions. So today I'll be talking about searching for distributions. It's based on two papers that we have. So the main motivation of this talk, or these two papers, is just like the trade-off between two notions of our resources when it comes to dealing with distributions. So one is, of course, like sample complexity. How much data do we need to solve some statistical task? But also, as a computer scientist, I also care about time complexity. How long does it take to solve this task? And so this talk is just about trade-offs between these two quantities for a natural problem, okay? And there'll be some, hopefully everybody will get a little bite out of this talk. There's some cool data structures, some sublinear algorithms, some lower bounds and stuff. So let's begin. So now let me define the formal problem. I give you k discrete distributions over the domain 1 through n. And let's say, these are v1 through vk. And what does it mean that, I'll give you these k distributions. And maybe I can pre-process them. I can build the data structure, kind of like in the classic algorithms world. And then much later, there's a query phase where I get sample access to some unknown distribution. And my goal is to output one of the k distributions that I know before that is the closest to it. Okay, maybe up to some small multiplier error and some small additive error. Okay, so that's the formal problem. And this is usually called hypothesis selection, density estimation, goes by a ton of names. Yeah.
Just for clarification, so in the pre-processing stage is the assumption that you could compute any function over these?
I'll get to that in a bit, what you're allowed to do in the pre-processing. And throughout the talk, of course, there's you cannot hope to get exact multiple error. There's always some additive error. So there's some epsilon parameter, but I'm just going to ignore its dependence, okay? Because it's kind of ugly in the bounds. So what does it mean that you're given access to these distributions? So what we're going to say is someone gives you the PDF vector for all these k discrete distributions exactly. So you have these k vectors exactly, know all the probability masses. And now what does it mean pre-processing, right? These are just vectors, right? So you can kind of do whatever algorithmic pre-processing that you want in any model of computation, right? Okay, every time maybe you can group the distributions by the probability values in the last domain element, for instance. Or you can do whatever crazy pre-processing you want, okay? Think of it like a graph algorithm problem, right? Like I give you a graph, you can pre-process it, and later you have to answer, say, shortest path queries. Here, I give you k discrete distributions. Later, you have to answer these sort of nearest neighbor distribution queries, okay? And one assumption I'm going to make, or the parameter regime I'm most interested in, is when the number of distributions is really large. It's much larger than the domain size. And the reason this regime makes sense is because if I give you if I give you, let's say, n domain elements, the number of different discrete distributions is actually exponential in n, right? You can think of a net on the L1 unit ball. So, it makes sense there are many, many distributions that you're searching over, okay? And it makes it more closely related to nearest neighbor search, which I'll get to in a bit. But this is just the parameter regime that I'm interested in. There are a ton of distributions, and you want to find the closest one, okay? And just to make sure everyone's on the same page, right? When I said the closest one, I meant in L1 distance. This is sort of the most natural way to measure distances between discrete distributions. It's the same as the TV distance up to some factor. And hopefully people are familiar with this. But just think of it as the absolute value of the coordinates, okay? So this is my problem. Later on, I'll actually work with the easier problem where this unknown distribution that I sampled from later is guaranteed to be one of the k, but I don't know which one, okay? Then the multiplicative error doesn't make sense, right? Because it's 0. So we're going for a small additive error. Okay? So this is a easier problem, but still, it's still a pretty interesting problem. Okay. And this is usually called the proper setting or the realizable setting. Any questions so far about the problem definition? I just give you some distributions, then I sample from one of them, and I have to figure out which one I'm sampling from, essentially. All right.
Just a question of the last one. So you're not going to look at three. Is that what you said?
Sorry.
You're not going to consider three in this talk?
Oh no. I am. All I'm saying is this unknown distribution. I'm going to assume it's sometimes I'm going to assume it's one of the k distributions that I had. So I'm just highlighting that in the sense that this makes
Oh,
it
I see.
slightly easier.
You're assuming that
Yeah.
this unknown one is close to one.
Yeah.
As opposed to a situation
Where it could be arbitrary. Okay, yeah. This is an easier problem, but still pretty interesting.
Just a question on that. I wonder if there could be a situation where there's also an option to say none of them, like nothing's close to what I'm measuring. Yeah, just like yeah.
Yeah, so
Could that be built in?
that could be built in, but it's kind of interesting. If you want to answer that kind of thing, the dependence on the sample complexity turns out to depend on the domain size. Here we'll see like this problem is well studied, so I'll get to the bounds about what people know. So the reason I like this problem a lot is because it kind of interpolates two very nice areas in theoretical computer science, statistics, and so on. One is sort of distribution testing, right? This is like a classic statistical problem, but also nearest neighbor search, right? Usually in nearest neighbor search, we just get vectors, right? And we want to find the closest vector to a query. There's no, all the vectors are known, essentially. Here, the interesting part is it's kind of like nearest neighbor search, but you have some, the distribution you're sampling from, you don't know it exactly, right? You only get sample access to it. So some version of noisy nearest neighbor search as well. Okay, so what do people know about this problem? Like I said, it's been extensively studied in both statistics and computer science. And essentially, like there's a long line of work, and I'm really like the dot is really pulling a lot of weight. There's a ton of work. Essentially, like one really nice result is that you can't solve this problem. And people have nailed down the sample complexity. The sample complexity is actually log k. It doesn't depend on the domain size at all, which is really cool. And it turns out, right, with log k samples, to this unknown p, you can actually find like a 3 approximation. So at a height in O1, up to some small additive error, and it only takes log k samples. Okay? So it's very sample efficient. It's like sublinear sample, right? Like you're not even paying attention to the domain size. But the runtime is actually kind of slow. Intuitively, what these algorithms do is they kind of want to eliminate each V1 through VK1 at a time. So they are performing some sort of linear scan over all the K distributions, okay? So, so this is one end, like where you just care about sample complexity. There is a very, very sample complexity efficient algorithm, but runtime wise, maybe it's not so nice, right? This is this is amazingly sublinear. This one is, you're performing a linear scan. There's also another extreme where the runtime becomes really very awesome. So what you do is you just take a shit ton, you take a lot of samples, and you learn the probability mass of every domain element very, very accurately. Then you don't really care about the sampling part, right? You just do L1 nearest neighbor search, right? You have this PDF vector. It's very accurate coordinate-wise, so you can just search the closest nearest neighbor in L1 distance. And that turns out you can actually solve this as the algorithmic problem, and the runtime is let's say square root of k. Okay, it's very sublinear runtime. So on one hand, right, we have like a very sample efficient algorithm. On the other hand, we have very runtime efficient algorithm, right? The query time is sublinear, but they kind of get really bad bounds in the other parameter we care about. Okay, so if I present this to you, right? Yeah.
In the second setting, if I have one P very accurately, why even bother trying to find one of the elements that's closest? Like, why would that be? Why would you just use P hat or whatever you call this thing?
Yeah, I guess there's two answers. One is like that's just the way I define the problem, right? You want to, but also like in some sort of applications of these problems, you actually it's like you want to output something that's among the K things. Maybe it's like that
P covers whatever policy.
Yeah, exactly. And you already only have a discrete choice of policies. Yeah, exactly. So if I present this to you, right, then the natural question to ask is, can you get an algorithm that's That's sublinear sample complexity. Internally it's saying it's not learning the distribution, right? We don't want to take a ton of samples so that it learns the distribution. We want to do something better than that. And also we don't want to do a linear scan over these K distributions that we know, right? We want to avoid some linear scan. Why is this beeping? Okay. Yeah, so can we do the best of both worlds? Can we get sublinear in both parameter regimes? Okay, so that's what we study. Any questions so far?
Sorry, just one more, like, it could be that K is like exponential n, as you suggested, in which case log K is like n.
Exactly, yeah.
But, so we're gonna look at something that.
Yeah, so we're
quite that big?
Yeah, we're thinking of K as like maybe polynomial in n. Like, if you have n to the 100 distributions, what can you do? Okay.
Yeah.
Okay, so our results are the first paper. We say we study this problem, and somehow we can get both sublinear sample complexity and sublinear running time, but just barely in a very funny way. And also not for the general problem where P is unknown, but where you're guaranteed that P is one of the K things. Okay. Okay. It is sublinear, but now let me show you the bounds. It's like hilariously close to not being sublinear. Okay. So essentially in the proper setting where we're guaranteed P is one of the DIs, right? We can actually output a distribution. Let's say using this many samples with that many query time. This is a little bit opaque, but essentially think of setting T to be like square root log K. Okay. Then this is sublinear in n. And this is kind of base logarithm rules, right? If I have 1 over log K to the 1 over log K, that's E. But 1 over square root of log K, that's not. That's you get some barely sublinear in K. Okay. Oops, what happened there? Let me actually draw it out because it's easier to see. Like right, this is the extreme where we just optimize for writing time. That is the extreme where we just optimize for sample complexity, and somehow we're like very much at the edge, barely sublinear in both. Okay. I thought I had the bounds written. Okay. But yeah, I mean, this plug in T equals like square root of log K. Sorry, I should have done that. And you get like barely sublinear sample. It's like a little bit less than n, right? Sublinear n. And you get sublinear in K too, right? K, T is square root of log K. K to the 1 minus 1 over square root of log K is barely sublinear in K. There's some log properties. And in the okay, once we saw that, we're like, okay, we worked very hard, but we got barely sublinear in both. Is that actually necessary? So the second paper, we show that under a natural model of computation, there is some inherent trade-off between the sample complexity and the running time. In particular, you cannot have an algorithm that has, let's say, square root of n sample complexity and square root of k query time, right? That's not allowed. So essentially, what we show is that any algorithm that takes like this many samples must have this query time if you're only allowed polynomial preprocessing under a natural computation model. Okay, we cannot prove unconditional lower bounds. That's that's P versus NP kind of. So under some natural model, which I'll explain in a bit, we can essentially see that like, okay, at least you either need to take many samples or we need to have large running time. Like we cannot save in both. Okay. Okay. So any questions so far? Yeah.
What if this set of distributions add some sort of nicer structure to it?
Yeah, so that's the funny thing. This lower bound is for a very nice class of distributions.
Really?
Yeah, so, oops.
Like I was just thinking, there's some hierarchical thing. Could that somehow be leveraged? Like you're saying,
Yeah, so what is a lower bound instance? It's essentially, I give you these K distributions. They're going to be half uniform, meaning they're going to be uniform over half of the domain elements. But I'm going to randomly pick which half. Like, I'm going to randomly pick half the domain elements. And the query is going to be one of these distributions. And my goal is to find, where it came from, essentially. And there's this natural computational model where even this very simple problem has this lower bound. Okay. And yeah, and then for this particular example, actually, we can get an upper bound that matches this as well. Just a small remark. Okay. So what is a computational model? Okay, it's not like the general model of computing is something called the list of points model. And this model is sort of motivated by the fact that many search algorithms, not just for distribution, but for general nearest neighbor search, fall under this model of computation. So it's kind of natural to prove lower bounds in this model. So essentially, I'm not going to give you the full, definition. Essentially, what you're allowed to do in the preprocessing, right? What kind of data structure are you allowed to build? That's what the model says. Essentially, you can take your input, K distributions, and you can partition them into buckets, however you please. And then when a query comes, you take some samples. You can adaptively choose which bucket to look at. And if the distribution you want to find happens to be in one of the buckets, then you're happy. And the runtime is measured in terms of like how many distributions did you kind of look over. Okay, so this is the model of computation. Okay, so this is not the formal model, but this is kind of the intuitive model. Like you're allowed to group distributions and adaptively look over groups when you get samples. So in this model of computation, we have a matching lower bound, or we have a lower bound. And you might think like, okay, what else can the algorithm do, right? This seems pretty natural. Turns out, yeah, this model of computation is not the end of the story. There's actually very recently there's a similarity search algorithm, not for distributions, just for general vectors. That's not in this model. So it does something really weird. But yeah, we can talk about that later if you want. All right. So essentially, just to kind of put it into pictures, right? This upper bound we had is barely not sublinear in both sort of running time, inquiry time, and sample complexity. And essentially, the lower bound says, okay, this big region inside is impossible. So somehow you either have to take a ton of samples, almost linear, or you have to have almost linear query times. So you're either almost linear distribution or almost performing a linear scan. You cannot save on both. Okay. All right, so I thought, so for the rest of the talk, let me kind of give you an overview of the upper bound. It's a very interesting and weird algorithm. So I thought it would be nice to present it. So let me go back to the problem, right? Like I said, you see these K discrete distributions. You can pre-process them. Later, you get sample access to one of them. And I want to output something that's close. Okay. That's my problem. So what is the high-level algorithmic intuition, right? What does it mean to search in sublinear time? Turns out, like in general, in the algorithms world, we can only search things in sublinear time if they look like norms. Okay, these are the only things that we have like sublinear data structures for, right? Like nearest neighbor search, L2 nearest neighbor search, these kind of things. So one natural idea, maybe if you're coming from stats, is like, okay, can you come up with a plugin estimator that maybe like, kind of captures this distance that we want to minimize. And if it looks like a norm, then, we can actually search for it, right? Algorithmically, then we're happy. The thing about these plugin estimators is that they're actually not very good. Like the estimators you have to design are very unnatural in some sense. So here's a very, very natural algorithm. Take some samples, form the empirical distribution of the samples, and let's say, okay, let's solve this optimization problem, right? Like I form this empirical distribution, find the VI that's closest to the empirical distribution. This actually does not work very well, okay? The reason is like the TV distance is very hard to approximate like this. So there's a natural example where this very intuitive algorithm just fails. So let's just say I have two distributions, is okay. One is uniform and one is only uniform on the first half element. And let's say I even take a linear number of samples, right? I take a ton of samples. Even then, this plugin estimator is not going to work. So these are my two distributions, right? One is uniform and the other is half uniform. And let's say the distribution I'm sampling from is actually this second one. One caveat is I'm going to sort of randomly pick which n over 2 elements is uniform one. And then let's say the empirical distribution looks something like this, right? I take S samples, right? The things I don't sample, I have 0. Things I do have, I sample, I get multiples of 1 over S, right? This is my empirical distribution. And the, what did I say? Oh yeah, sorry, you get samples from the uniform distribution, not the half uniform. And the point is like the things that you do see, right? It's actually closer to the wrong distribution than the right distribution, right? If I, right, basically, 1 over S, which is the probability mass on my empirical distribution is actually closer to the wrong distribution than to the right distribution. So essentially what ends up happening in this example is that you can show with constant probability, like either this is small or this is small. Like they're both equally likely to be smaller than each other. So that means you're just getting the wrong distribution like 30% of the time. Okay. So that's kind of intuition about why these like plug-in estimators don't work. Okay. Okay. So now we do something slightly different. Okay. How do we design a good algorithm? Turns out the one intuition that we had was, okay, you need to kind of separate out two types of probability domain elements. Those where this unknown distribution has large mass, and those where it has very small mass, okay? And the main reason is any estimator that you design, these like probability elements that have large masses will cause it to have high variance for those estimators. And that sounds bad. But the cool thing algorithmically is that these heavy elements are very easy to detect, right? You just see a ton of them. So you can just maybe filter them out. Whereas these light elements, right, things that don't have much probability mass are hard to find when you sample. But they, if any plugin estimator that you may create, they'll only contribute small variance because the probabilities are small. That's kind of the intuition. So we algorithmically exploit this like small probability mass versus large probability mass behavior. Okay, so before I present the algorithm, it's a really weird algorithm. Let me kind of tell you what's going on. We're going to use like something called L-infinity nearest neighbor search to filter out these high probability domain elements. And then we're going to actually perform a finer search using L2 nearest neighbor search on these light elements. And the really weird thing is like, well, I really care about the L1 distance, right? But somehow I'm using like two very different distances as a proxy for L1. Okay. Any questions so far about the high-level plan? Okay. Okay, yeah, so yeah, this is kind of roughly halfway. So, quick stretch before I present the algorithm. Welcome to join me. All right, let's keep going then. Okay, so what is the preprocessing? It's very natural. I'm gonna bucket my K distributions into groups. And how am I gonna define the groups? Essentially, every group will have distributions that are very, very close in L-infinity norm, meaning all their probability masses are very close to each other. Those are my groups. So maybe V1 will have a group, right? The L-infinity ball looks like a square kind of. And then V2 will have a group. The groups may will overlap. That's okay. VK will have a group. Okay. So that's my preprocessing. I just group distributions that are similar. And then inside every group, right, I can take the leader of the group, which is the distribution that defines the group, and I can use that as a way to figure out which domain elements are heavy and which are light. So I say, okay, for this group, right, if I look at the probability masses and the domain elements that have this much probability mass, I call them heavy. The rest I call them light. These numbers don't really matter. It's just that I'm breaking my distribution into groups, and I'm defining heavy or light with respect to every group. Okay. And now, what is the query algorithm? I take some samples, I form this empirical distribution. Then I find the group that's most relevant to me, right? And how do I find that? I find the group, the lead, I find the distribution that's closest to my empirical distribution in L-infinity norm. Meaning I find the distribution where the worst case difference is the smallest. Okay. And within that group, I do a different kind of search. Within that group, I switch my norm to L2 norm. And I find, inside the group, the closest thing to the empirical distribution in L2 distance. Okay, so I'm doing this like two-phase thing. But inside a group, I throw away the heavy elements. I just look at the light elements. Okay, so that's my entire algorithm. So now let's see what it looks like pictorially. And let's say these red dots were my K distributions, right? I pre-process them and everything. I get some samples, right? This is the blue dot, right? Then I do this L-infinity, Then I do this L-infinity search, right? Which means what is the closest thing to p hat in L-infinity distance? Let's say it's V1. And remember in V1, right? V1's group was only V1 and V2. We threw away everything else. So inside the group, I do a different search now, right? I switch to L2 distribution, L2 norm, which looks like a ball, right? So inside, I do a different kind of search. So that's the main algorithm. Oops. Why does it keep doing that? Okay. And I didn't tell you about the quality of the search I'm doing inside, but essentially it doesn't really matter. I'm just trying to find the best. There's, but yeah, that part doesn't matter. I'm just looking, first finding a group to narrow down my answer to, and inside a group, I'm doing a very fine search. That's all I'm doing. Okay. And the main intuition is like the first search that I do, where I do this L-infinity search, it kind of helps me figure out which the heavy elements are of my unknown distribution, right? And then I can kind of throw them away. And then I can just focus on the light elements. Okay, that's the idea. Okay. Any questions before I present the analysis?
I think this is one of the square root of epsilon or something.
And the 1 over square root of n has to do with the fact that I take almost n samples. I take like, let's say n over log n samples, barely sublinear, barely not learning the distribution. Maybe n over, log n to the 100. Something, almost linear, but barely sublinear.
I guess I was just, if it happened that all of the distributions were just in one group.
Right.
That radius.
That's fine.
Then all you're finding is the best L2 thing, not the best L1.
Yeah. But it turns out that's in that case, they're almost the same. Turns out in that case, yeah.
That must have something to do with.
Yeah, exactly. Yeah. But forget about the parameters and whatever. All I'm doing is grouping the distributions and just switching norms when I search inside. Okay, that's all I'm doing. So there's 3 claims, right? One is like, let's say the true thing that I want, let's say B star, must be in the first group that I find. If it's not, then we kind of feels like we've already lost it, right? We already lost the plot. So that's the first thing we have to show. The second thing is, once we narrow down a group, we can actually throw away the heavy domain elements. We don't care about them anymore. And the third thing is, searching only the light elements will return a good answer. Okay, that's what we have to show. So let's look at the first one. Because I'm taking so many samples, I'm taking almost n samples. N is the domain size. I'm taking maybe barely sublinear n. It turns out, a standard concentration bound will show that the empirical distribution will approximate the true unknown distribution, kind of pointwise up to this 1 over root n error. This is actually not enough for L1 guarantees, right? Because you get n times 1 over root n. That's meaningless. But it's still useful. So it's saying, in the first stage, I already know that I'm approximating the true probability thing very, very closely. Not as close, to solve the problem, but still very closely. The L-infinity nearest neighbor search, right? What guarantees does it have? It finds the best answer in L-infinity, right? That's the algorithmic problem. The best is actually better than the true, right? But I know the true is small, right? By the previous guarantee. So that means, right, the distance between the best thing I find and the true thing I'm looking for is, this triangle inequality, right? And each of these terms are bounded, right? This is better than this because, right, algorithmically, this is smaller than this, right? I found the best. Whereas this is small because I'm taking a ton of samples. Essentially, all this is saying is that in the first pre-processing, right, where I group the distributions, whatever I found, the group I found actually contains my true answer. Okay. That's kind of why I set this threshold, but it doesn't really matter. These are some numbers that come up in the calculation. The next thing we claim is that once I narrow down the group, I can throw away the heavy elements. Okay. And really the reason is, okay, I know an element was heavy if it's bigger than some threshold. Okay. And the intuition is like, okay, on the heavy elements, right? On every element, I'm getting error of something like 1 over root n now, right? Because I'm approximating my unknown thing up to point y 1 over root n. But there aren't too many heavy elements, right? There's only n to the 1/3, which is smaller than square root of n. So this kind of goes away, right? We can just throw away all the heavy elements. Because I'm approximating all the heavy elements so accurately, I can just throw them away. Now, the interesting thing is, okay, now I've narrowed down to a group, right? At this point, I've kind of ensured that, I kind of know what for all the heavy elements, I've kind of found a good answer. That's everything in the group is a good answer if I just care about the heavy elements. But I also care about light elements, right? Because they could contribute most of the TV distance. So there is a really nice estimator, which is this. S is the number of samples. turns out that if I just look at the empirical distribution, and I just take this like expectation of this thing squared, like what sub-elements, I'm just looking at the light domain elements now, right? It's not too difficult to see that the expectation is actually related to the L2 distance. Okay. So now let's just pretend the expectation is the reality, right? We have to show it concentrates, but let's just pretend it's the reality. And essentially, right, on the light element, this estimator has expectation S. On the heavy elements, right? Sorry, for the true thing, this estimator is S. For everything that's bad, right? Everything that's far away that I don't want, right? This L2 to L1 thing tells me it's this, right? This is the L1 to L2 conversion. Cauchy-Schwarz. But the ratio between the true answer and the bad answer is this thing, right? And this is exactly the quality of L2 nearest neighbor search I'm doing, right? That's what I'm saying. Like in the second space, I'll find that I do L2 nearest neighbor search very, very finely, almost exactly. And the reason is like it turns out, right? In the good case, it's this value. In the bad case, it's this times the good, this value times this. So if I find an approximation that's a little bit better than this, I'm guaranteed to find a good answer. Okay, so that's kind of why in this L2 part, I need to do a really, really fine search. Yeah. And like, how do we, kind of combine everything? Well, the intuition is, okay, the heavy elements are taken care of because I approximate them pointwise. There aren't too many of them. And the light elements are taken care of. So, kind of if I sum them, everything is fine. That's all I'm saying. Of course, this is only in expectation. I need to show it with high probability, but the main reason is like all the probability masses are small now. So it turns out this estimator actually has really good concentration because there aren't any heavy probability masses. You get really good concentration inequalities. So, I could have just used this identity in the very beginning, but it turns out it doesn't concentrate very well if the probability masses are large. Yeah. Okay. So the query time is only dominated by the search I'm doing, right? This L1 and L2 nearest neighbor search. The L1 nearest neighbor search turns out it's fine. It's almost free. But it turns out like to do this quality of L2 nearest neighbor search, the best running time we have is something like this. So if you do 1 plus C approximation, you get K to the 1 minus C. So, if you want to do exact, you have to pay linear time. So the runtime, the query time is actually this, where S is the number of samples. So essentially, right, I want to make this sublinear in K, right? So I just take S to be N over some log factors. So it is sublinear in K. And, it's still also sublinear in N, right? So, right, this is barely sublinear in N, right? This is barely sublinear in K. That's how you get best of both worlds, but not in a very, not in a very satisfying way, but you still get it. And the cool thing is, okay, essentially, right, the previous algorithm has this kind of performance, but we show that in some natural model of computation, you must get, like you cannot get truly sublinear. You cannot get square root of K here. That's kind of the main point. Okay, so let me give you some quick intuition about the lower bounds. But before I do that, any questions? Yeah.
Just curious about the choice of template 1/3 of this heavy light filter stuff. Is that, where,
That's not really important. It's just something smaller than square root of N. Okay. Any other questions? Happy to give some intuition again about the problem. Yeah. If not, let me just tell you about the lower bound. It's kind of a separate story. So here's a very hard problem. I give you these K discrete distributions. Each of them will be half uniform, meaning they're going to be uniform on half the domain elements. But I'm going to pick the half randomly for every one of them. Okay. So now, this, if I plot like kind of our upper and lower bound. So the x-axis is like sort of, the fraction of samples used. The y-axis is the query time. Essentially, our lower bound. So this is a plot of our function. It's saying like if you take very, very few samples, then you must have a really high running time. The green dotted thing is the upper bound I just presented. the green shaded thing is the upper bound for our special lower bound instance. Okay, so you can get a better upper bound for a special case, obviously. And the point is like if you zoom in into that corner, these two lines will meet. So, or like they'll get very close to each other. So somehow this region is like the impossible region. Green is possible. There's still some like unknown in the middle, but if you kind of zoom in, they'll actually kind of meet a little bit. Okay. I won't have time to tell you about the lower bound, but just to get an intuition about how you even prove lower bounds, right? In general, like you have to make assumptions to prove lower bounds. So you start with, maybe 10 years ago, 20 years ago, someone wrote a paper that says, this is an assumption I'm going to make. That's where you start with, right? You want to show that your, whatever people assumed is a special case of your problem. So your problem can only be harder, right? That's how lower bounds work. Like I said, right, to show lower bounds, you take another hard problem that people think is hard and show that it's a special case of your problem, right? So your problem can only be harder. So what is this other hard problem that people had studied? It has nothing to do with like distributions, but it's still kind of interesting. It's called like correlated search. And the problem is I give you k binary vectors where each entry is like some coin flip. And then I draw another binary vector that's correlated with one of these k vectors, but I don't know which one, slightly correlated, like entry-wise. Okay. And I want to find the correlated pair. That's the hard problem. I didn't tell you the parameters, but you can imagine, right? There's a parameter of how correlated they are and what is the, how you draw the things and so on. But this is the intuition. Turns out there is actually a very recent work, relatively speaking, that shows that this problem is hard in this list of points model. That's where we started with, and our goal is to show that our problem is only harder than this. And it kind of makes sense, right? Here, you still know all the vectors. For us, we don't know the entry of the vectors, right? That's the sample. We only have sample access to this unknown distribution. Yeah, so, but this turns out this problem is a special case of the distribution testing problem, if you look at it in a right way. And the main idea is like, if we take very few samples in our problems, it kind of corresponds to this correlated search problem where the correlation is like very weak. So it's like it becomes a harder problem in some intuitive sense. But I won't be too formal about it because it's too annoying. But essentially, that's what allows us to get a lower bound. We just take this existing lower bound and show that's a special case. Yeah. But the main message of this talk is, there is like an interesting statistical computational trade-off for an interesting problem. And the cool thing I find is like this trade-off is only apparent when you want sublinear requirements in both. Okay. There are lots of papers that study statistical computational trade-offs, but usually those papers are trying to distinguish between polynomial time versus like exponential time. Here it's like, if you just care about polynomial time, there are no trade-offs. But if you look at this like data structure world, like, in regular data structure world, we want sublinear runtimes. Then you see this like really weird phase transition almost. Yeah, I think that's all I have. But yeah, happy to take questions and thanks for listening.
Upper lower bound, that's 1 over
Right.
versus 1 over log.
Yeah.
Which one do you think is loose?
It's really hard to tell. Yeah, so there are a bunch of upper problems. Yeah, one of them is this lower bound versus this. I think this is the right answer. But there's also another big open problem here, which is this upper bound algorithm we had. You need to assume that the unknown distribution is one of the k things that you have. That's the assumption. But this problem you can consider in a general case, right? Where this P is not one of the VIs. Then our algorithm actually does not work at all. Yeah, so our algorithm is like really, really exploits the fact that that it's one of the VIs. Yeah, so that's another open problem. Another problem is like, okay, you can ask similar questions for different types of the distances. Yeah.
So in a sense, that of the algorithm, we start with the
Yeah.
You probably have that, hopefully you not drop them, you start the KNN for both heavy and light.
In some sense, like inside a group, you're kind of promised that if you only care about the heavy domain elements, all the distributions are close to each other. So it doesn't really matter which one you output. So that's why like you can drop it. The computation complexity is actually just like, because we say the domain size is kind of small relative to number of distributions, it's sort of dominated by like how many points are in a group. And that could be up to K. You don't know, everything could be in the group. But yeah, I mean, yeah, that's, I don't think it would help.
Just thinking back to the example of uniform versus uniform array. What's heavy, light, those cases, they're all.
Yeah, so yeah, in that case, there's no heavy light. That example was more to show that like if you just use the plugin estimator, which just looks like what you want to search, that would not work. But in that case, actually, the second step would be very efficient of our algorithm.
So you just basically do L2.
You just do L2, yep.
And
that's-
somehow that
yeah.
doesn't have the problem of
Yeah.
distinguishing those like L1.
Yeah, exactly. Yeah. So that's a weird thing in distribution testing. You often find that like if you care about TV distance, people design estimators that look like L2 distance, which somehow turns out to be a much nicer quantity in this world. Any other questions? Not. Thanks for coming and enjoy more pizza.
Yeah.